Think about something you do every single day, probably without a second thought. You turn on the tap, fill a glass, and you trust what comes out. But have you ever stopped to wonder why you can trust it? What really makes that water safe? Well, let's dive in.
It's such a simple act, right? But that trust is actually built on a huge, complex, and honestly, mostly invisible system of protection. Because if you go back in time, trusting the water was a massive gamble.
I mean, for basically all of human history, the answer to, can I drink this, would have been a very hesitant, maybe. Having access to clean, safe drinking water is a pretty modern luxury, and getting it wrong could be absolutely deadly.
And this is why. These are the invisible dangers that were lurking in the water. For centuries, water was the main superhighway for devastating diseases, things like cholera, typhoid, dysentery, all caused by tiny little pathogens you couldn't see, taste, or smell. This was the problem that desperately needed a solution.
So, how in the world did we get from that scary reality to the point where we can just turn on the tap without fear? Well, here in the United States, the answer lies with a dedicated watchdog and a really solid set of rules designed to keep those invisible threats out of our cups.
The main player on the field here is the Environmental Protection Agency, the EPA. They're the ones who literally write the rulebook for safe drinking water, and these standards apply to all public water systems across the entire country.
And this whole system isn't just a simple thumbs up or thumbs down. It's actually a lot more nuanced. For every single potential contaminant, whether it's a bacteria or a chemical, the EPA establishes two critical benchmarks. And it's how these two numbers work together that really protects our health. This is the secret sauce.
Okay, so let's break this down, because this is the heart of the whole thing. On one side, you've got the MCLG. That G stands for goal. Think of this as the perfect, ideal, and a perfect world number. It's the level where there's zero known health risk. It's a target, not a law. Then on the other side, you have the MCL, and that's the level. This is the law. This is the line in the sand. It's the legally enforceable limit, and it's set as close to that perfect goal as technology and feasibility will allow. So you have the ideal target, and you have the enforceable law.
So when we use this word contaminants, what are we actually talking about? The list is pretty long, and it's incredibly varied, all designed to build this comprehensive shield against a whole bunch of different threats.
We're not just talking about a handful of things here. The regulations cover more than 90 different substances. They get broken down into all sorts of categories, everything from living microbes and disinfection byproducts to a whole spectrum of inorganic and organic chemicals. It's a really extensive lineup.
Let's look at a couple of examples so you can see how this works in practice. We'll start with a biological threat a lot of us have probably heard of, E. coli. This is a classic example of a microorganism that the EPA keeps a very close eye on. Now here's the interesting thing. E. coli itself isn't always the big danger. Its presence, which comes from human or animal waste, is basically a giant red flag. It's an indicator. It screams, hey, the door might be open for other, more dangerous germs. And because of that, the law is super strict. If more than 5% of a water system samples pop positive for total coliforms in a month, that's a violation. Period.
Okay, so that's a bug. Now let's switch gears from biology to chemistry and talk about a heavy hitter you've definitely seen in the news, lead. This is an inorganic chemical, and it poses a completely different kind of threat.
The problem with lead, which usually gets into water from old pipes corroding, is its long-term health impact, especially for kids. It's so serious that the health goal, the MCLG, is zero. Zilch, nada. So the law here works a little differently. It uses what's called an action level. Think of it like a tripwire. If more than 10% of homes tested have lead over 0.010 milligrams per liter, the water utility must take action, like treating the water to make it less corrosive so it doesn't dissolve the lead from the pipes in the first place.
And here's what's so crucial to understand. This system isn't just stuck in the past. It has to evolve, because the threats to our water are always evolving too. And there is no better example of this than the recent challenge from a whole new class of chemicals. I'm talking about PFAS, which you've probably heard called forever chemicals. These are man-made chemicals that were used in, well, almost everything, from nonstick pans to firefighting foam. The problem is right there in the nickname. They just don't break down. Not in the environment and not in our bodies. And we're only now really beginning to understand the health risks. So as the science caught up, the EPA had to act. They just recently established a brand new, legally enforceable limit for PFOA, which is one of the most common types of PFAS. And the number they landed on is this. Just look at how incredibly small that number is. To even try to wrap your head around how tiny that is, try this. It's the equivalent of one single drop of liquid diluted across 20 Olympic-sized swimming pools. It just goes to show you how incredibly precise these regulations are becoming as our science gets better. It's a perfect example of the system adapting in real time.
So, after looking at the history, the system, and these new challenges, what's the big takeaway? What does the future look like for making sure our trust in the tap is always a safe bet? Okay, let's pull it all together. What we have in the US is a really strong science-driven system. It's all built on that clever two-part idea of a perfect health goal and a practical enforceable law. This framework is our shield against over 90 different contaminants, from bacteria to lead. And most importantly, as we saw with PFAS, it's designed to be a living system, one that evolves to tackle new threats as they appear on the horizon.
And that really leaves us with a final big question, doesn't it? We depend on this powerful, invisible shield every single day. But as our science uncovers new things and our world keeps changing, this system is going to face new tests. So the question for all of us is, what's it going to take to make sure this shield doesn't just stay strong, but stays ahead of the curve for all the generations to come?